The axiom of countable choice or axiom of denumerable choice, denoted Axiom, is an axiom of set theory that states that any countable collection of non-empty sets must have a choice function, i.e., given a function A with domain n such that A is a non-empty set for every n, then there exists a function f with domain n such that f(A) for every n. The axiom of countable choice is strictly weaker than the axiom of dependent choice, which in turn is weaker than the axiom of choice. Paul Cohen showed that Axiom is not provable in Zermelo-Fraenkel set theory without the axiom of choice. Axiom holds in the Solovay model. ZF plus Axiom suffices to prove that the union of countably many countable sets is countable. It also suffices to prove that every infinite set is Dedekind infinite. Axiom is particularly useful for the development of analysis, where many results depend on having a choice function for a countable collection of sets of real numbers. For instance, in order to prove that every accumulation point X of a set SR is the limit of some sequence of elements of S, X, one needs the axiom of countable choice. When formulated for accumulation points of arbitrary metric spaces, the statement becomes equivalent to Axiom. For other statements equivalent to Axiom, see Herlich and Howard and Rubin. A common misconception is that countable choice has an inductive nature and is therefore provable as a theorem by induction. However, this is not the case. This misconception is the result of confusing countable choice with finite choice for a finite set of size n, and it is this latter result that is provable by induction. However, some countably infinite sets of non-empty sets can be proven to have a choice function in ZF without any form of the axiom of choice. These include V (-O) and the set of proper and bounded open intervals of real numbers with rational endpoints. Use as an example of an application of Axiom, here is a proof that every infinite set is Dedekind infinite. Let X be infinite. For each natural number n, let n be the set of all 2n elements subsets of X. Since X is infinite, each n is non-empty. A first application of Axiom yields a sequence where each Bn is a subset of X with 2n elements. The sets Bn are not necessarily disjoint, but we can define CO equals BOCn equals the difference of Bn and the union of all Cj, j less than n. Clearly each set Cn has at least one and at most 2n elements, and the sets Cn are pairwise disjoint. A second application of Axiom yields a sequence with Cn, so all the Cn are distinct, and X contains a countable set. The function that maps each Cn to Cn plus 1 is a one-to-one map from X into X which is not onto, proving that X is Dedekind infinite.